In this video, we're going to take a look at electrical switchgear. I'll explain to you exactly what switchgear are, why we have them, the different parts and components that make up typical switchgear. We'll look at different ways to classify switchgear. And finally, we'll use an interactive 3D model to take a look at some medium voltage switchgear. Switchgear are designed to protect electrical components and equipment within the electrical system from things like short circuit faults and overload faults. The main purposes of switchgear are control, regulation, and protection. But the one that most people think of when they think of switchgear is protection. We don't want voltage surges, current surges passing through our electrical system freely. We want to arrest any short circuits or overload currents before they damage the equipment and components within our electrical system. It's switchgear that allows us to do that. Switchgear is usually classified as low voltage, medium voltage, or high voltage. Sometimes you may see another classification, which is extra high voltage or ultra high voltage, but generally the type of switchgear that you'll see if you visit an industrial plant will be either low voltage or medium voltage. If you're working in substations, then yes, you will move on to high voltage and extra high voltage or ultra high voltage. The definitions concerning exactly what low voltage, medium voltage and high voltage are differ depending upon your geographical location and also upon regulatory bodies. IEC, IEEE, ISO, NFPA, all of these organizations issue guidance notes concerning what exactly low voltage, medium voltage and high voltage systems are, what pieces of equipment they may contain, how to maintain those systems, etc. As a general rule, if you're looking for some quick guidance concerning what LV, MV and HV systems are, low voltage is typically anything less than 1000 volts. Medium voltage will be in the range of 1000 to 70,000 volts. High voltage will be 70,000 up to maybe 220,000, and anything above that will be classified as extra high or ultra high. Keep in mind though that extra high and ultra high may not exist, all of that may just be referred to as high voltage. These definitions also differ depending upon the industry you're in, because if you work in a substation and everything is above 110,000 volts, then everything is high voltage. For this reason, sometimes they change these definitions to make them more appropriate. It may be that they refer to low voltage as something being around 70,000 volts. In an industrial setting though, these limits of 1000 and less for low voltage, 1000 to 70,000 for medium voltage, and above 70,000 for high voltage can be considered roughly correct. In this video, we're only going to focus on low voltage and medium voltage switchgear. If you want to learn a little bit more about high voltage systems, we have videos on substations and all of the equipment within a substation, and I definitely recommend that you check out those videos. But before we go any further, what exactly is switchgear? Throughout this video, you may hear me refer to a switchgear or simply switchgear. I apologise for the confusion, it's just sometimes when I talk about switchgear, I talk about a switchgear, and if it's plural, perhaps the switchgear. Sometimes it's quite difficult to separate between the singular and a plural concerning switchgear, so I apologise if that comes across in this video. Returning to my question though, what exactly is switchgear? Well, switchgear is not really a single item. It's a group of components that have been assembled together that represent a switchgear. We can refer to all of these perhaps as a switchgear assembly. Switchgear has two main parts, the power conducting part and the control system part. The power conducting part is the part where our primary circuit, our primary electrical system, is flowing. If we've got a 1000 volt system and we have switchgear installed within that system, then our primary circuit is a 1000 volt circuit. The power conducting components within the switchgear would include things like switches, circuit breakers, and fuses. These are the parts that conduct or interrupt the flow of electrical power. Switchgear also has a control system side. The control system side is there more to monitor and control the power conducting components, the components within our primary circuit. Items that you'll typically find within the control system are things like current transformers, potential transformers, also known as voltage transformers, protective relays, and other electronic items that help the switchgear fulfill its purpose of regulation, control, and protection. The control system side of the switchgear is almost always at a much lower voltage than the power conducting side. If we're looking at switchgear that's installed within a 1000-volt system, then the power conducting components within our switchgear have a voltage potential of 1000 volts. The control system components will not have a voltage potential of 1000 volts. They may instead utilize a more common voltage potential such as 24 volts, 110 volts, 220 volts, etc. The higher the voltage on the power conducting side, the larger the difference will be in voltage potential between the power conducting side and the control system side. There's a good reason for this. If we were operating a system at 30,000 volts, we don't necessarily want to send 30,000 volts to our protective relays and other electronic systems. So we use the control system in order to get a signal from the power conducting side of the switchgear at 30,000 volts and convert that signal to something that's a bit easier to work with. We convert the signal using current transformers and potential transformers, and then we pass these signals onto things like protective relays. The protective relays can then decide if there's an overvoltage or overcurrent event and open and close the circuit breaker depending upon the signal they receive. Circuit breakers are designed to open whilst energized. That is to say that circuit breakers are designed to interrupt an electrical circuit. When you switch a light switch on and off in your home, you are opening and closing an electrical circuit. When the light is on, the switch is closed and we make our electrical circuit. When we open the switch manually, we break the electrical circuit and the light is off. Circuit breakers do this automatically, although there is an option to do it manually if you wish to do so. Unlike in your home though, if you are working at high voltages, which typically have large current flow, that is to say a high level of amps, it is not so easy just to open the circuit. When you open a circuit at higher amps and higher voltage, you will get an electrical arc, and this arc can actually be quite large, and it may give off a lot of heat. We need to extinguish this arc as quickly as possible. Switchgear can be further classified based upon how we extinguish this electrical arc. It's quite important to extinguish the electrical arc as quickly as possible. If we open up two contacts and the only insulating medium around the contacts is air, because air itself is classified as an insulator, then the arc will be extinguished, but it may take some time. What we're looking for is a better insulator than air. The most common alternatives to air that you're going to see include compressed air, oil, a gas such as sulfur hexafluoride, also referred to as SF6, and vacuum. So there are four main insulators that we can use to insulate the electrical contacts so that when they open, when they separate, the electrical arc will be extinguished as quickly as possible. Air, oil, vacuum, and gas, SF6 being probably the most popular type of gas that you're likely to see. SF6 is also referred to as a type of gas insulated switchgear, or GIS, and there are several gases that fall under this GIS category, carbon dioxide being another, although it's far less common than SF6. When you're looking at switchgear, keep in mind that low voltage switchgear is always air insulated. You don't need oil, vacuum, or SF6 to extinguish the electrical arc at low voltages. When we're looking at medium voltage switchgear, that's when we begin to use oil type switchgear, vacuum type switchgear, and gas insulated switchgear, such as SF6. If we go into the high voltage range, you're more likely to encounter gas insulated switchgear. Let's take a quick look now at a low voltage circuit breaker, and then we'll take a look at a low voltage switchgear room. Here is a low voltage circuit breaker. This is the front part of the circuit breaker, the bit that you would see normally if you were looking at it within the plant. This is the side here, which you wouldn't normally see. The bit at the back, which connects to the bus bars. The side again. And here we are again, standing in the position of where the operator would stand. You can see that we've got some indications here concerning if the breaker is open or closed. Got buttons here such as push to close. We've got a lever here which we actually use to put tension on a spring. That spring is then used to open or interrupt the electrical circuit. You can see here that the spring has been discharged. So all of these little indicators here help us to understand what the position is of our circuit breaker. Notice now that we're talking about a circuit breaker and not switchgear. Circuit breakers are the part of the switchgear that's used to open or close a live circuit. Switchgear includes the circuit breaker, but also other components as well. Switches, fuses, current transformers, voltage transformers, all of those are the things that we would refer to when we talk about switchgear. Notice we've got a nameplate over here, low voltage AC power circuit breaker, tells us the amps, frequency, model, and other important bits of information that are supplied by the manufacturer, usually. Here we've got our protection relays, although these look a little bit blurry. Protection relays decide when the circuit breaker should operate based upon the signals it gets from items such as the current transformers and voltage transformers. The protection relays that we're looking at here, these are digital protection relays. There are two types you're going to see: digital protection relays, which are also referred to as solid state protection relays, and electromechanical protection relays, which are the older type. Low voltage breakers often use electromechanical protection relays. They're cheaper and it's quite acceptable to use them for lower voltages, although this one here has digital protection relays. Once we go to higher voltages, we start to use digital protection relays because they're more accurate, and the tolerances when we open and close our circuit breaker might need to be much more specific than when we're operating at lower voltages. The circuit breaker itself is just retracted. It can be pulled out, for example, from the right side towards the left, and then we can just insert another one of the same design, the same type, to replace it. So they're modular in design, they're easy to replace. When we pull them in and out, we call this racking. On the newer designs, there are also safety interlocks to ensure that we're performing this operation correctly. Let's have a look at a low voltage switchgear room. Here is a low voltage switchgear room. We would enter through the door here, which you can just about see. Notice that we've cut a hole in the floor here so that you can see the cables coming in. Cables go off and they will come underneath the cupboards here. You can see our low voltage breakers, slightly different design, but you can see here contacts open, ready OK, spring discharged. You can also open or close the breaker manually, and we've got this lever here where my mouse is for charging up the spring. These circuit breakers are modular in design as well, and we can pull them out and replace them quite easily. This is a low voltage switchgear room if we consider all of the parts that are involved in the system. The room itself is protected by a fire suppression system. That's these red bits of piping here. And we've also got a smoke detector here because we want to protect the items within this room as much as possible. And that means that we need to have some sort of smoke detection in case there's a fire or maybe a smouldering event within the room. Let's now take a look at some medium voltage switchgear. Here is our electrical room again. This time we've got medium voltage switchgear installed within the room. Here are some digital protection relays. The top part of the switchgear is where all of the control systems, the low voltage part of the switchgear, is housed, and the lower part here is where our power conducting parts are housed. We've got this mimic diagram. This diagram here is called a mimic diagram, and that helps us understand exactly what's happening within our switchgear. Come over here, you can see another mimic diagram, and again, and again. What exactly though is within the medium voltage switchgear? Let's take a look at a vacuum type medium voltage switchgear. Here is a vacuum type medium voltage switchgear. This is how it would look from the side, although you wouldn't have access to this, from behind. And then over here, we've got one side, which is our cutaway or cross section. Let's do a quick run through the components. At the base of the switchgear, we've got our voltage transformers, also referred to as potential transformers, which are a type of instrument transformer. They're going to measure the voltage on this conductor here and convert that voltage to a lower voltage and pass the signal onto items such as our protection relays. We've got some cables that come in here. We've got an earthing switch here, or one per phase. They're usually interlocked with the circuit breaker itself. Here is our vacuum circuit breaker. The contacts within each of these cylinders are maintained under vacuum, and we're going to open and close those contacts, and we'll have our arc within each of these cylinders. When we want to remove the circuit breaker, we can do so quite easily. It's similar to the low voltage circuit breaker. It's modular in design. We just retract it. We pull it out from right to left. And as we do so, the earth switches change position also because they're interlocked with our circuit breaker. What will also happen is when we retract the circuit breaker, shutters will automatically close and seal this compartment so that there's no connection through this barrier. So the shutters will seal roughly where this line is now, and we'll also have separate shutters down here which will seal where this line is now. These shutters make it simply safer for personnel. We've got current transformers here, also a type of instrument transformer. They're also going to measure the voltage and convert it to an electrical signal, which we can pass on to our protective relays and other electronic devices. You can see here that these electrical conductors come upwards. They will then go to our cylinder with our contacts inside this vacuum cylinder, and then we'll have other conductors which will come along here, and then they'll pass upwards and begin to form our buzz bars. These buzz bars look to be insulated already. You can see that here. The buzz bar, the electrical conducting part, would be this aluminium piece here. I guess aluminium, or if it was a different color, maybe copper. And around it we've got this sheath, this polymer based material, and that is an insulator. If we come up here, you can see that the compartment is sealed off. So the buzz bar compartment is sealed off completely, as is the circuit breaker compartment here, and as is also the low voltage compartment, which is this compartment here. That's where we have our electronic control devices and our lower voltage electrical systems. The protection relays will also be mounted within the low voltage compartment. I hope you now understand how we classify switchgear, what components make up switchgear, and what the functions of switchgear are. If you want to use any of the 3D models shown in this video, then head on over to saVRee.com. We've got over 400 engineering 3D models that you can use directly through a web browser in AR or VR. If you want to learn more about engineering, we've got over 45 hours of engineering video tutorials and courses at saVRee.com, and you can learn about valves, pumps, power stations, electrical transformers, and many other common engineering machines and processes. Before you go, don't forget to subscribe to the YouTube channel. Thank you very much for your time.